Hi everyone. This lesson is about Leslie matrices. Leslie matrices are used in the study of population dynamics, and the reason they're called Leslie matrices is because in 1945 a mathematician by the name of P.H. Leslie wrote this paper on the use of matrices in certain population mathematics. So this is a good and interesting application of matrices. So let's begin with this example here. We have the following profile for a population of tribbles. For those who aren't sure, use Google. Tribbles are a fictitious little creature from Star Trek. Now, these tribbles, we've divided the population into three age groups, and then the 200 is the total number of tribbles in age group 0 to 3, the juveniles. There's 150 in the middle age, and there's 90 of them in their old age, and none of them live past 9 years of age. We're going to assume that the tribbles are 50-50 male and female. So that 200 there, for instance, is 100 males and 100 females, and so on. Now, in order to calculate with these things, we set up a thing called a Leslie matrix, and it's a 3 by 3 matrix. There are three age groups, that's why it's 3 by 3. And the first row of the table is the birth rate. So the birth rate 0, 1.4, and 0.4. Now, what do those numbers mean? Well, the 0 here means that none of the triples in the 0 to 3 years of age produce offspring. They're too young. The 1.4 means that for every female tribble, not the males, for every female tribble in this age group, at the end of every 3-year cycle, they have produced 1.4 offspring. So some would have 1, some would have 2. Maybe some would have more, but it would be rare. And then in the 6 to 9 year age group, only 0.4 tribbles are produced per female in that 3 years. So that's the birth rate. The survival rates here get written on a sub-diagonal, not the main diagonal. So we start from the next row and with 0.6, then we drop down diagonally 0.8, and the other entries of the matrix are filled in with zeros. So let's just highlight that again. The birth rate goes in the first row. The survival rates go in a sub-diagonal, and that's the Leslie matrix. Now, as long as the assumptions that the population is not affected by natural disasters, or the population has sufficient food resources to grow, and maybe there's no migration, so there's no tribbles coming from other areas or tribbles leaving this area. So in this particular little geographical location, those numbers in that matrix represent the way the population changes from time to time. And the times would be jumping ahead in 3-year groups because we're using 3-year age groups here. Now let's talk about the population vector. And we'll call it P0 for the original. And the population vector is the numbers 201, but we only want to count the females. So I'll be halving those numbers. 100, 75, and 45. Now, why only the females? Well, the females only because it's only the females that reproduce, and our first row of the Leslie matrix is about reproduction. It would be pointless to put a reproductive rate of 1.4 for the entire population because only half of the population reproduce. So now, how do we calculate the population at some time in the future? So after one time period has elapsed, in our example, it would be 3 years. We multiply the Leslie matrix by the original population vector. So I can do that on my calculator. I've got this already written in to save time. So there it is, and when I hit enter, my answer is 123, 60, 60. So I'll just write that one down. The population was 123, 60, 60. Now remember, that would represent the number of females. So instead of 100 juvenile females, we're now up to 123. Instead of 75 middle-aged females, we're down to 60. and instead of 45 old age females, we're up to 60. If I want the total population of the tribbles, I'd have to add those three numbers and then double them to account for the males. Now, something interesting happens if I look at population 2. That's the Leslie matrix, just times population number 1. And again, I can, well, actually, let's do something a little bit more mathematical. Wasn't population 1 just the Leslie matrix by P naught? And wouldn't that be best written as L squared by P naught? So P2, the population after 2 time periods has elapsed. We could calculate this if we just go back and modify to put squared, L squared, and that's the original population. So I have 108, 73.8, and 48. It's a bit funny to talk about fractions of a tribble, isn't it? So what have we got there? 108. Then the next one was 73.8. I'll put 73. I won't round up, I'll truncate the number because it would mean there hasn't been enough time for the 74th tribble to be born yet. So, and then I'll have 48. So that would be population vector number 2. Now, more generally speaking, we could write that population after n time periods is the Leslie matrix to the power of n multiplied by the original population vector. That's good. Now, we will find, I think, if we look at this example here, just looking at the younger ones, we went from 100 to 123 to 108. So the numbers are going up and down a little bit. If we jump ahead a long time, we will get, I think, a much more stable population. So if we jump ahead to say population after 50 time periods, I would want the Leslie matrix to the power 50 times P naught. Then I'll compare that with 51. So a fairly large jump, but then the very next consecutive one. Now I'll just get my calculator going over here to do that. So I just have to go back and change that power to a power of 50. And there's a pretty good number. Again, I'll truncate these. So 230, 136, and 107. 230, 136, and 107. Now, I'll just pause while I do the next one for you. Okay, so there's the population vector after 50 cycles and after 51 cycles. Now, remember these numbers only represent the females, don't they? If I wanted to know the growth factor, we sometimes talk about the growth factor, G, or the growth rate of the population. So I would need to have the total population, wouldn't I, after the 51. So the total population at 51, subtract the total population after 50 cycles to get the actual increase, then make that a fraction of the original value. I'll just pause while I fill the details in. Okay, so there we are. What I've done for the growth factor is I have added together all of those and doubled it to give the number 958. Then for the previous one, I have added together all of those, remember they're just the females, and doubled it, and that gave me the 946. So I'm looking at the actual increase after one cycle compared to the one the one at the beginning there, the P50. Now that calculation comes to the decimal 0.127, which could be expressed as 1.27%. So we have here, after a long period, so the population has stabilized. It looks like our population is growing at the rate of 1.27% for every 3-year cycle in the process. Now, that's about enough for now, I think. That gives you the basics of Leslie matrices. The most important thing to remember is where those different numbers go. The birth rate in the first row, the survival rate in the subdiagonal, the population vector, it's a column vector, that's going to be just the females. So the total population, we typically assume 50-50 male, female. It could be otherwise, but if it was otherwise, it would have to be stated for you in the question you were working on. And then, of course, we can do any calculation we like. The long-term growth rate, growth rates can be positive, like the one here, where the population increases. Sometimes growth rates are negative. Sometimes after the population stabilizes, the total number is declining, and sometimes it's stable. So that's enough for this time on Leslie matrices. Thanks for watching.